In this video, I'm going to be going through Chapter 4 of Preliminary HSC Engineering Studies, or Year 11 Engineering Studies. Chapter 4 is Biomedical Engineering, and we're basing this on Engineering Studies, The Definitive Guide, Volume 1 by Paul Copeland. We're looking at questions 1 on, and so they look like this. I won't be referring to the questions too much, but I will be posting my answers. So there are answers, but I think it's for a lot of the worded questions, there aren't really answers. So this is where I like to go through them to give you an idea. This was set as homework. It was due today, so I will put these answers up. I'll put these answers up after the due date. Okay, so first of all, what do biomedical engineers do? They facilitate the development of production of devices that assist the diagnosis and treatment of medical conditions and devices that assist people with medical conditions. That's a bit of a mouthful, so rather than me reading it out, I'm just going to try and say in my own words. Okay, so what do? They make stuff and they develop stuff. So that means they make it better, they produce, they implement, they maintain stuff. What kind of stuff do they make? Stuff that helps people who are sick, people who have medical conditions. Right, so they treat medical conditions, they diagnose medical conditions, and they assist people with medical conditions. They can also work on things like prosthetics, which are artificial organs or body parts to, again, assist people who have medical conditions. Okay, so I didn't want to flick back and forth too much, but what health and safety matters must they consider? Well, I think I asked this question somewhere in my Google Docs earlier, is that they have to consider okay. Sorry about that. Biomedical engineers must consider biocompatibility of their devices so they're not rejected by the patient. They need to ensure that their devices do not expose patient staff or researchers to health risks. And they must ensure that implements do not fail during the service life due to the risk to the patient. So I remember seeing a thing about a guy who he had a device that was beeping inside him, couldn't sleep because it was beeping like once every 90 seconds. He couldn't have it removed because the surgery was done overseas. It was a bit of a problem for that guy. So definitely you want to make sure that you minimize the negative impact of the devices on people's quality of life. Okay, so what are some biomedical innovations? They include neurocommunication, so like Neuralink, which is what Elon Musk is working on, to control devices or allow devices to directly send signals to blind patients. So we have when it's in people's ears, we call those cochlear implants, but now people are working on bionic eyes. We have prosthetic arms that we are trying to be able to simulate the sense of touch. There's some innovations, but there's a whole bunch of less interesting things like innovations in insulin pumps for diabetics, things like delivery of medicine through implants that sit inside your stomach or maybe closer to so rather than taking an aspirin, if you have a chronic condition, we can actually implant something that releases paracetamol to the source of the problem in much lower doses. Even things like UIDs for like contraception. Okay, there are a number of ethical issues that are faced by biomedical engineers. The biggest concern is testing. Testing on animals is a big concern. Another thing is that there's use of radioactive materials, which people don't like. They don't like nuclear reactors. There are people who oppose the nuclear reactor in Lucas Heights, even though we wouldn't have any chemotherapy drugs without it, or it'd be 10 times as expensive. People who feel as though biomedical technologies violate the natural order and the development of these technologies can negatively impact on patients in trials. So some people who are like, well, this experimental trial actually made my father's life worse in the last 3 months of his life. That might be an answer. We also talked about things like the deaf community opposes cochlear implants. Well, I don't want to speak for the entire community, but there are sections of that community that are post-cochlear implants. So there's some ethical considerations. Here I have produced a timeline of biomedical innovations. It's a short one, but I've discussed that several times, so you can read. I don't need to read that for you. Okay, so I don't really understand the context of this question, so I'm going to go here to Abiomed's AbioCore is a major advance in total artificial hearts. Why? So they were important because it's self-contained, meaning it wasn't an external machine, meaning it greatly improves the quality of life of the patient and reduces the chance of infection. So what are some of the impacts of biomedical innovation? Well, increase in lifespan, patient comfort, mobility, mobility in terms of the activities that people can perform, ability to communicate and interact in society. These technologies can be, so these impacts can be negative. So nuclear waste, we said that radiotherapy is a biomedical innovation. It carries some small amount of nuclear waste, and that is a concern that people have. People generally have, but generally these impacts we consider to be both positive socially and economically. Okay, we've got some questions on mechanical advantage. So we'll look at the question. I don't need that, but I'm going to keep ticking on it to it accidentally. Okay, what is the velocity ratio, or what is the mechanical advantage of this question? I went through this, I walked through this when we first talked about this. I highlighted how you would approach this question. And we'd say, well, the load and effort. We know mechanical advantage is load divided by effort. I'm not going to find the sheet here because I want to try and cover this as quickly as possible. Load over effort is 25 divided by 20, which is 5 over 4, which is 1.25, would be the mechanical advantage is 1.25. There you go. Okay, velocity ratio is the distance traveled. Now, this is a first order lever, right? Or in the class of levers, it's a first class lever. So that means that the fulcrum is in between the load and the effort. Now, for a first order lever, you can have a mechanical advantage that could be more or less than 1. In this case, we have long handles. And so the long handles mean that the distance of the effort is where the human applies their effort or where the engine applies the effort. In this case, it's a human applying the effort, so the load is going to be longer. Now, when we say mechanical advantage is load over effort, when we do velocity ratio, it's the other way around. It's the distance of the load, so distance of the effort divided by the distance of the load. The distance of the load here is 120 mil divided by 75. Let's have a look, right? So now, I've actually used pi r here. You don't need to worry about the fact that there's a pi in the... Why? Because the 2 pi, or I mean, the 2's and the pi's, they both cancel out. So if the 2's and the pi's cancel out, it doesn't matter. Now, what's interesting is... So I said the distance of the effort divided by the distance of the load. Sorry, I think I misspoke when I spoke about that a second ago. I don't need that. I'm going to close that. The distance of the effort divided by the distance of the load. So 75 divided by 120 is 0.625. So in this case, we're actually having to put in more effort than we get out of the thing. This is actually useful because forceps, they clamp onto babies' brains. So you maybe want to put on, you actually want to apply less effort. That's an argument. But more importantly, what you want is reach. You want reach. That's what you're looking for, and precision, rather than when we have a mechanical advantage less than 1, we're not getting a mechanical advantage in terms of our force. There's no force advantage. What you're getting is a precision advantage or a reach advantage. Okay, so this one here, we're going to look at efficiency. Now, this is a tougher question. I'm not going to go into this here because I've gone through this question on YouTube. This is a question that there's maybe a 1 in 10 chance that I would put this in a preliminary exam. It's a hard question. It's not an unreasonable question. So the argument would be that although it's not explicitly in the syllabus, this sort of question, you can derive it from first principles. And the fact that there's an example in the textbook, when I say an example, there's not a worked example, there's only this question. And I have given the worked solution on YouTube. So if you want to go through that, you can do that in later. I'm not going to go through. I mean, I've got the working out, but I'm not going to go through it in this video. Okay, so now we're going to talk about forging. Why is it better than an artificial hip? We see this question all the time, right? So this is a really common question. You should have discussed in the biomedical engineering report. This is a really common question in exams. And so the idea is that forging produces a grain structure that follows the shape of the insert, whereas a machine insert will have points of weakness, right? So because when we machine things, the grain flow it's in a straight line. And so that means that the tip of the stem could be a point of weakness. Ingot casting, I don't really like questions on ingot casting. As in, when I say I don't like something, that means that I haven't seen it a lot in HSC questions. And I think I've seen it once or twice, but it's not a very common question. It's not something I use as a question a lot. So with the age of diagrams, explain the process of dendritic solidification. This is in the textbook. Oh, okay, so I skipped one. Okay, it consists of 4 steps. Nucleation points, dendrites develop. Dendrite is Latin for little tree. Secondary arms form, grain boundaries form where the dendrites meet. Now, there's a diagram in page 134. I'm not going to go to that diagram now because I don't want to flick around. I'm trying to be fast in my answers here. But what I'll say is we've also looked at videos. We've looked at the same video several times. The video is linked in a couple of places, but I know it's linked on the annealing video. It's right at the start. You can watch when they cool some aluminium and the dendrites form. When we do our dot point revision, I'm happy for people to say, hey, I don't really understand those 4 steps. Could you please explain them? But I'm just going to plow through on this question at the moment. So next one, draw and label the structure of a result of an ingot cast in sand versus one that's cast in metal. Okay, so I really will have to go to ingot casting. See the books. Here we go. See the book for the difference between casting between sand and metal. When you call in sand, you have these little small chill zone crystals, right? And then you're going to have smaller, more equiax crystals. When you cast into metal, what you're going to have is just these long column-like columnar grains, right? That's what you're going to get when you cast into metal, and you won't probably get any of this small equiax grains in the middle if you cast into metal. So that's the difference that you can look at when you compare those two. Investment casting consists of, okay, so I guess this question is asking about investment casting. Does it say that you should have a diagram? No, just as described. A diagram wouldn't be bad, but there is a diagram if you look on page 143. It says investment casting consists of, first of all, what you do is you make the thing out of wax. Then what you do is you coat the wax in ceramic. You then melt the wax out of the ceramic, so the ceramic is now hollow. Then what you do is you pour the steel into the ceramic and then you tap away the ceramic, and then after that you're left with you reveal the casting. Okay. I will just point out that it's now 11:30, so for people who are going to if they have a class next that's on Zoom, they're free to go to that class. But I'm going to continue, and I will be recording the rest of these answers as well. So, okay. Heart valves are not forged. They are welded to eliminate risk of weld failure, as welding causes distorted dimensions. So why would we give a reason why heart valves are forged, not welded? Yeah, welds can have points of weakness. Welding can also have welding doesn't have good dimensional accuracy. Outline the different stainless steels. Select a suitable application for each. Now, this is a question I will not write in any exam I write, because there just hasn't been enough questions on stainless steel in exams. So for the stainless steels, I just say, well, for starters, you can look at the notes on page 145, 146. We talk about the different kinds of stainless steel, martensitic, austenitic. We talk about those in other notes in a video that I've recorded previously, and there's notes that attach to that. I've left it very simple, this answer, because I want to reinforce this is not something I go into in a lot of detail. Okay, precipitation hardening. This is a thing that this is a question on the rise. This is something I'm seeing more and more. Explain the heat treatment process for precipitation hardened stainless steel. Okay, so it is on page 146 where you can see the diagram. Yeah. I don't know why I went into so much detail talking about tantalum and niobium, but anyway, let's have a look. Steel is quenched and then reheated at about 600 degrees Celsius that allows precipitates to form, strengthening the steel. Again, I go into that in a lot more detail in that video. I'm not going to go through it here. You really need to draw a diagram. Generally, what you would say is that there's a process of, well, first of all, you cast the thing and then you cool it, you reheat it, and then you cool it again, and then you heat it again for a lower temperature, right? And then you cool it for a long time. That's why it's also called age hardening. So when you reheat it, I'm not going to go into the phases, right? So what you'll do is you'll produce an alpha phase and a beta phase. What this does is we heat it up until the point where the alpha phase is completely, the beta phase is completely, it completely disappears. It recrystallizes and it just becomes part of the alpha phase. And then what we do is we cool it and then heat it slowly for a long time so that when the beta phase reappears, the beta phase will reappear as micro grains, like microscopic grains, evenly dispersed throughout the alpha phase. That's, again, even that's a lot of detail. We cover precipitation hardening again in year 12, but if you're not happy with that answer, go back to the video on ferrous metals. That will go into a lot more detail. We also need to know that aluminium is the big one that we can precipitation hard, and alloys of niobium and tantalum are also precipitation hardened. I couldn't remember that if I hadn't been reading that, but moving on. Okay, so going to the question of why do we use polyethylene for an artificial hip joint? This is something you should have done if you did the engineering report. It says that polyethylene, we use ultra high density polyethylene, or UHDPE, is used for hip and knee joints for its excellent impact resistance. Walking around puts a lot of impact on things. Even small repeated impacts are enough to create problems. The polyethylene provides high impact resistance. Okay, so we're talking about cracks and why we include partially stabilized zirconia to inhibit crack growth. When cracks pass through the, okay, so what happens is we talked about it's metastable, which is the example people use is if you pour sugar into a cup and then put it in the microwave, and then if you put a spoon into that cup, the water will actually like violently erupt from the cup. And that's because what happens is the water actually wants to change phase. It wants to go into a gas, but it can't. It doesn't have an opportunity. There's not enough nucleation points for it to go through the phase change. So what we have is superheated liquid. And when something happens, when that's disturbed, so if you put, say, a spoon into the cup, what happens is that the disruption causes that change in phase to happen very, very quickly. And when it happens very, very quickly, it erupts as water, or hot steam that can splash out and burn you. In this case, what we have is metastable zirconia, and so that when a crack starts to enter into a region where there's metastable zirconia, is that this allows the zirconia to have rapid change in phase, and it expands when it changes the phase. And what that does is it occupies the volume that was being the volume that was left by the crack. Okay, so takes up more space, closing the crack, preventing its growth. There we go, moving on. Okay, question 20 is some sort of question about electronics that I don't really take a lot of interest in. What is the length of the wire to provide the power rating? Don't like this question. I've given the answer, but I don't like it. You can follow the solution I've given. That's pretty much all I want to say. Okay, 21. Find the power of an appliance that uses 8 amps and 12 volts. Well, we know that power equals voltage times current. Now, when we say voltage these days goes by a new name. It goes by electromotive force. So you can remember that as pi or PEI, P-E-I, whatever you want to remember, right? PIV, however you want to remember that formula. The last couple of years, the HSC has written the formula as P equals EI. And I think that's just to test people's knowledge to know whether or not E stands for electromotive force. Anyway, so in this case, it's pretty easy. Power equals current times voltage. So current is 8, voltage is 12. 12 times 8 is 96. Okay, so, and what is the unit for power? Oh, I didn't even write it there. Watts. You can notice I wrote P equals VI. It can also be expressed as other ways. You might remember I have a circle. It's four different colors, and it expresses all of the different formulas in different ways.
Oh, I think you wrote the answer in kilowatts there.
Ah, okay.
5,625 watts.
Okay, excellent. That was actually... Sorry, that's for the next question. So we're actually at 21. 12 times 8 equals 96 watts. But it looks like I've written the answer here in kilowatts. I haven't written the unit, which is bad practice. Unfortunately, it's a PDF, so it's too hard for me to change it. So we're just going to have to accept that that's the way it is. Okay, so what we have here is we've said that power equals voltage times current. The problem is, what if they give you a resistance? Well, in that case, you need to go to... I have a diagram with... it's a pie diagram with circles. I don't care enough to look for that diagram now. I'm just going to say that there's another formula, which is you can rearrange Ohm's law and this formula to get power equals current squared times resistance. And that is going to give you, once you multiply those numbers, you'll get... I think I've just taken the answer straight out of the book is where I've got that number. I think that Copeland may have provided that number in the answers. But thank you for letting me know that it is actually in, it's probably in kilowatts, given that this number is big and this number is being squared. So 25 squared, 25 times 200 is going to give us an answer of 5,000. So thank you. Good catch. That answer really should be written in watts, not even in kilowatts, ideally. Okay, the next question says we have doing a continuity test. Determine the value required for the resistor to not if we don't want the amps to exceed 20 milliamps. So let's have a look at our question. We've said that V, so we should know Ohm's law is V equals IR. We should be able to rearrange that to say R equals V divided by I. So the resistance equals the voltage divided by current. So in this case, what is the voltage? We've got voltage is 9 minus 2. Okay, so the voltage drop across each LED is 2.5. Oh, okay, we've got 9 volts and we've got 1.5. Interesting. I've got 1.5. Wouldn't it be 3? Oh no, 2 times 1.5. There we go. Good work, Luke. It's actually, yeah. I mean, it is correct, but in my haste, I didn't say it's not 9 minus 2, it's 9 minus 3, because there's 2 1.5 ohm resistors. Well, effectively they act as resistors. Sorry, 2 1.5 voltage LEDs. So what we have is a total of 6 volts. 6 volts divided by the current, which was 20 milliamps, gives me an answer of 300 ohms. More information on that is on page 149, 150, but really it's just Ohm's law and application of Ohm's law. Okay, so this question, question 24 says, demonstrate how 3 NAND gates can be constructed to produce an OR gate. Then demonstrate how 6 NAND gates can be used to produce an XOR gate. Did I produce an XOR gate? I did not do the XOR gate. Interestingly that I do. Okay, so that's tough. Well, I remember when I first did these questions before I found the answers for things. What is tough about this is that for A, what you need to have is both inputs come from A and both inputs come from B. And that's not very intuitive, right? People were not used to seeing that. The point is, what is interesting is that you can take NAND gates and you can wire NAND gates to produce anything. My understanding of biology is that your brain has something like 100 trillion synapses, and that synapses effectively act as a NAND gate. If you make an XOR gate, now we don't really get XOR gates, but you can make an XOR gate from NAND gates. So how do you make an XOR gate from NAND gates? There you go. I mean, I didn't verify it, but I'd say it's correct. Anyway, so What features of a drawing are not sectioned? Okay, so this is interesting. Section drawings are not hatched. Section drawings are not hatched even when the section cuts through certain features such as voids. Yeah, this is worded badly. What I should say is section drawings are not hatched when, so I shouldn't have the word even. The word even makes this confusing. They should not be hatched when the section cuts through certain features, such as voids. So if there's an opening, right, like the difference between when I asked you to draw the picture of an apple compared to if you're drawing an apple of drawing of a capsicum, that bit of air that's in the capsicum, you don't section that because there's nothing there. Webs. So when we talk about webs, what we're talking about is like the pith in the capsicum. The pith is a different color. So where we section the capsicum by drawing the 45-degree lines where it goes through the red part of the capsicum, we don't section the pith, right? Because it's just a web. It's stiffeners. If there's thin sections, and we don't want to mislead people. We don't want them to think that there's this great big solid section of capsicum which isn't there. It's just actually only a very thin section. It's just anyway. We also don't shafts. So if we have, like, say, steel rod, actually, if it's hollow, if it's a solid rod, would we section? I don't think so. And bolts, we definitely don't section. No part of a bolt or a nut do we section. So we don't section. We draw the hex bolt as a couple of lines. Anyway, this is all detailed in page 157. It's important to remember that you keep your hatching evenly spaced, or you'll lose marks. Now, when I say that, I've now had discussions with senior engineering teachers about drawings, and I don't know if that's as true as it used to be. But these days, if you did the thing freehand, you'd probably be okay. But you should try to make sure that they're reasonably consistent in the spacing. Certainly doesn't have to be accurate to the nearest millimeter, but I would try and keep it consistent spacing as best I can. That's the answers. Thank you for those of you who stuck around, especially the person who gave me some help with correcting that should be kilowatts. If anyone had any questions, I'd be happy to answer them.
I had a question with, it was the long mathematical one, question 20.
Yep.
Where did you get the PLA from?
Okay, so this letter here is not a P. Okay. That letter is a rho. It's the Greek letter rho, and it's used for a couple of things. It's mainly used for density, but it can also be for resistivity. Resistivity is like the idea of when we talk about how well a material conducts, like, so silver is the best conductor, then copper, then gold. So we would measure, like, we actually measure, usually we talk about the resistivity as a fraction of 100 as pure copper. So silver actually has like 100 and something percent, whereas gold is 90 something percent, whereas aluminium is also in the running. Aluminium is a little bit less good conducting. So that should have been given in the question, what that value for resistivity is. What we're trying to find is the length, and then we have the area. So what we're trying to do is we're trying to say that we know that resistivity equals voltage squared divided by power, right? So here I have P equals VA. That's not right. It actually should be P equals VI, right? And that we know that if we know power, P equals V squared. So we can rearrange that equation. We can say that we know that power equals voltage squared divided by resistance. And we can rearrange that calculation to then get, so resistance equals this. Now, resistance is measured in ohms, but the ohms can be calculated by resistivity divided by the volume of the wire. So that's what L and A are. L and A relate to the volume. So generally I like A for area, except in this case that'd be confusing because A could also be confused with amps, especially the way I've written those answers here. That really should be I. There should be no A, capital A there. Anyway, so what we're trying to do is calculate the volume of the wire. We calculate the volume of the wire by knowing its length and cross-sectional area. So you've got the cross-sectional area. So if you know the resistivity must have been given. We said it was question 20?
Yeah, it is. Yeah, it's 103 times 10 to
You got it. Anyway, it's reassuring to know that I will never write a question like this, just because we haven't seen questions like this enough.
I didn't know how to do it. I had to look at the answers.
Fair enough. Does that answer your question?
Yeah.
Cool. I will ask you, the three of you or the four of you, to stick around just for a second after I hit stop.